Helicopters are amazing machines. Unlike airplanes, they generate lift using rotating blades. These blades, called rotor blades, are like long, narrow wings. When the rotor blades spin, they create lift. This lift is what allows a helicopter to take off, hover, and fly in any direction. The faster the rotor blades spin, the more lift they generate. To move forward, the helicopter tilts slightly, directing some of that lift forward. To hover, the lift force must equal the helicopter's weight, keeping it perfectly balanced in the air. Now let's talk about dissymmetry of lift. This is a crucial concept in helicopter aerodynamics that affects how helicopters fly and maintain stability. Imagine you're riding a bicycle and there's a strong wind blowing from the side. You have to lean into the wind to keep your balance, right? You feel more force on one side of your body than the other, right? This uneven force makes it harder to ride straight and requires constant adjustments. That's kind of what happens with helicopter rotor blades. The rotor system has to deal with similar forces, but in a more complex manner. As the helicopter moves forward, the rotor blade moving in the same direction as the helicopter, known as the advancing blade, experiences a higher airspeed. This increased airspeed generates more lift on that side of the rotor disc. Meanwhile, the rotor blade moving opposite the helicopter's direction, called the retreating blade, experiences a lower airspeed. This reduced airspeed results in less lift on the retreating side. This difference in airspeed creates an imbalance of lift on opposite sides of the rotor disc. This is dissymmetry of lift. To counteract this imbalance, helicopters use various mechanisms, such as blade flapping and cyclic pitch control, to ensure stable flight. Understanding dissymmetry of lift is essential for both pilots and engineers to design and operate helicopters safely. Why does this happen? Think about it. The advancing blade speed adds up with the helicopter's speed, resulting in a higher relative airspeed. The retreating blade, however, is moving against the helicopter's motion, resulting in a lower relative airspeed. It's like swimming with the current versus swimming against it. This difference in airspeed creates a difference in lift. The advancing blade, experiencing higher airspeed, generates more lift. The retreating blade, experiencing lower airspeed, generates less lift. This unequal lift distribution across the rotor disc can cause problems if left unaddressed. Imagine a seesaw. If one side is heavier than the other, it'll tilt. Similarly, the helicopter wants to roll towards the side with less lift, the retreating blade side. This rolling motion is undesirable and can make the helicopter difficult to control. So we need some clever engineering solutions to counteract this dissymmetry of lift. Section 5. Effects of dissymmetry. Stalling out. One of the biggest dangers of dissymmetry of lift is the possibility of retreating blade stall. As we discussed, the retreating blade experiences lower airspeed. If the helicopter's speed increases too much or the angle of attack of the blades is too high, the retreating blade's airspeed can become so low that it no longer generates enough lift to support its portion of the helicopter's weight. This is called a stall. Retreating blade stall is a serious situation that can lead to a loss of control. Thankfully, helicopters are designed with features to prevent this from happening. Section 6. Countering, dissymmetry flapping and feathering. Dissymmetry of lift is a phenomenon that occurs in helicopters due to the difference in airflow over the advancing and retreating blades. This can cause instability and uneven lift, making it challenging to maintain smooth flight. To address this, helicopters employ two primary mechanisms: blade flapping and cyclic feathering. To combat the undesirable effects of dissymmetry of lift, helicopters use ingenious systems like blade flapping and cyclic feathering. These systems work in tandem to ensure that the helicopter remains stable and controllable, even in the face of varying aerodynamic forces. Blade flapping allows each blade to move up and down independently. This movement is crucial because it helps to balance the lift generated by each blade as it rotates around the rotor hub. As the rotor spins, the advancing blade, generating more lift, naturally flaps upward. This upward movement is a direct response to the increased aerodynamic forces acting on the blade as it moves forward through the air. This upward movement reduces its angle of attack, which in turn reduces its lift. By decreasing the angle of attack, the blade generates less lift, helping to balance the overall lift distribution across the rotor disc. Meanwhile, the retreating blade, generating less lift, flaps downward. This downward movement is essential for compensating for the reduced aerodynamic forces acting on the blade as it moves backward through the air. This downward movement increases its angle of attack, increasing its lift. By increasing the angle of attack, the blade generates more lift, which helps to balance the overall lift distribution across the rotor disc. This flapping motion helps to even out the lift distribution across the rotor disc. By allowing each blade to adjust its lift independently, the helicopter can maintain a more stable and controlled flight. Cyclic feathering, on the other hand, allows the angle of attack of each blade to be adjusted as it rotates. This adjustment is made possible by the helicopter's control system, which continuously monitors and adjusts the blade angles to ensure optimal performance. As the blade advances, its angle of attack is reduced, decreasing lift. This reduction in lift is necessary to prevent the advancing blade from generating too much lift, which could destabilize the helicopter. As the blade retreats, its angle of attack is increased, increasing lift. This increase in lift helps to compensate for the reduced aerodynamic forces acting on the retreating blade, ensuring that the helicopter remains balanced. The combination of blade flapping and cyclic feathering helps to keep the helicopter stable and controllable, despite the challenges posed by dissymmetry of lift. These mechanisms work together to ensure that the helicopter can fly smoothly and efficiently, providing a safe and reliable means of transportation. Section 7. Dual rotors, teamwork makes the dream work. Some helicopters, like the iconic Chinook CH-47, utilize two main rotors that rotate in opposite directions. This configuration, known as a tandem rotor system, effectively cancels out the dissymmetry of lift inherent in a single rotor system. As the rotors spin in opposite directions, the advancing blade of one rotor counteracts the retreating blade of the other rotor. This synchronized movement balances the lift forces on either side of the helicopter, resulting in a more stable and controllable flight. Section 8. Different helicopters, different challenges. While the basic principles of dissymmetry of lift apply to all helicopters, the specific challenges and solutions can vary depending on the helicopter's design and purpose. For example, a small lightweight helicopter designed for agility might experience less pronounced dissymmetry of lift compared to a larger, heavier helicopter designed for lifting heavy loads. Similarly, helicopters with advanced rotor systems, such as the fenestrine tail rotor found on some Eurocopter helicopters like the EC-135, might require different approaches to managing dissymmetry of lift compared to helicopters with more conventional tail rotors. Section 9. Safe flight. Respecting the imbalance. Understanding dissymmetry of lift is crucial for pilots and engineers alike. This phenomenon occurs because the rotor blades of a helicopter experience different relative wind speeds during flight. The advancing blade, moving in the direction of flight, encounters higher airspeed and generates more lift, while the retreating blade, moving opposite to the direction of flight, encounters lower airspeed and generates less lift. This imbalance can cause significant handling challenges. Pilots need to be aware of this phenomenon and how it affects helicopter handling, especially at higher speeds. At higher velocities, the dissymmetry of lift becomes more pronounced, making it essential for pilots to adjust their control inputs precisely. They must be adept at using the cyclic control to manage the tilt of the rotor disc and ensure smooth, stable flight. They need to understand how to control the helicopter effectively using cyclic feathering and other flight controls to counteract the imbalances created by dissymmetry of lift. Cyclic feathering involves adjusting the pitch angle of the rotor blades cyclically to balance the lift across the rotor disc. This technique is vital for maintaining control and stability, especially during complex maneuvers and high-speed flight. Engineers, on the other hand, play a vital role in designing helicopters that can mitigate the negative effects of dissymmetry of lift. They work meticulously to develop rotor systems that can handle these aerodynamic challenges. By incorporating advanced materials and innovative designs, engineers strive to create rotor blades that are both strong and lightweight, enhancing the overall performance of the helicopter. By carefully considering factors like blade design, rotor system configuration, and flight control systems, engineers can ensure that helicopters remain stable and controllable throughout their flight envelope. They analyze aerodynamic data and conduct extensive testing to refine their designs, ensuring that the helicopters can perform safely and efficiently under various flight conditions. In the end, respecting this aerodynamic imbalance is key to unlocking the full potential of these incredible flying machines. By understanding and addressing the challenges posed by dissymmetry of lift, both pilots and engineers contribute to the safe and effective operation of helicopters, allowing them to perform a wide range of missions with precision and reliability.